Hello everyone, welcome back to another tutorial. So in this tutorial we're going to be covering quiz 4 and I'll try to think of a better way to name it than was on eClass, and the best way I come up with best name I could come up with is vector operations, part 1, because quiz number 5 also deals with some vector operations, so I guess I'll call that one part 2. So the nice thing about this quiz is it's almost just a review of Eng 130. So if you guys remember Eng 130, we dealt a lot with vectors having to do with the magnitudes and directions. Well, this is going to be mostly the same, but the terminology is a little bit different in continuum mechanics, just, to make it sound a little bit smarter. But you guys shouldn't find it too bad. So with that being said, let's jump right in with the theory. So for the theory, we're just going to consider a nice practical example where we have two vectors, x and y, and they each have two components, x1, x2, and y1, y2, and we're going to discuss the operations that we're going to be looking at in this quiz. So looking at the first one, we call it the Euclidean norm. But if you guys remember back to Eng 130, we just called this the magnitude because it is simply just the length of the vector. And in order to find the magnitude of a vector, or the Euclidean norm in this case, sounding really fancy, all we do is we take the two components, square them, add them together, and then square root them. So it's kind of a nice formula as you guys see there. Finding a Euclidean norm should be a nice easy midterm question for you guys. Just throw the components of the vector right into the formula. Getting a little bit more, I say, complex in air quotations because it's still not that bad, we have the Euclidean distance. So this is the distance between two vectors. So if we look right here, we see that rho xy is a function of both the vector x and the vector y. So to get the distance between these two vectors, we basically use the same Euclidean norm formula above, but instead of just x1, we substitute that with x1 minus y1 and then x2 minus y2. So again, pretty straightforward formula. It's basically just plug and chug up to this point. And to finish the quiz off, we're going to be talking about the Euclidean dot product. And you guys might just remember this as the dot product. And what the dot product is used for is just to give us a sense of kind of geometry between two vectors. Because usually at the end of the day, what we use the dot product for is to determine the angle between two vectors. So if we look right at this formula, we have x dot y. And what we do is we just take the two components and multiply them together. So we got x1 times y1 plus x2 times y2. And what this is equal to is the magnitude of x times the magnitude of y. So that one's really nothing special. But then we have cosine theta. And that theta right there is the angle between two vectors. And that's what usually makes this so special, is we can find the angle between two vectors by taking the dot product. In just kind of a special case right here, if we were to dot a vector by itself, so let's say we go x dot x, well, we got x1 times x1 plus x2 times x2. And then what we end up is with the magnitude of x squared. And you notice how there's not a cosine there. And that makes sense because if we're dotting the same vector, well, the angle between those vectors is 0. And you take cosine of 0, you get 1. So it kind of just disappears. But remember that cosine theta, because that's going to come in handy when we start looking at the questions. So with these formulas kind of out of the way, you guys may feel a little bit refreshed. We can start jumping right into the quiz questions. So the quiz itself is composed of 3 questions, each dealing with one of those formulas that we just discussed in the theory. So the first question says, consider R2. So by R2, it means 2 dimensions. With the Euclidean norm, and then it shows the formula for the Euclidean norm as follows. And it says, how many vectors have, and then part A says, a norm of equal to 1. So norm equal to 1, well, that means the length of the vector must be equal to 1. So let's look at this kind of this grid here, and let's just put for fun, oops, I did the eraser. You guys will see me do that lots. So for fun, let's just put some labels. So let's say we got 1, 1. On this side, we got -1. And then over here, we also have -1. So how many vectors have this length? Well, if we're starting from the origin here, and actually let's put this as, let's go, red is the same as the origin, that won't help. All right, let's go blue. So if I were to have a vector that goes from here to here, we know that this itself has length 1. We can just tell visually that that has length 1. We can have another vector that goes straight up. So from the origin straight up here, and we can tell visually that these ones have length 1. And we can quickly verify that because if I were to do the coordinate points of this vector, it goes 0 in the horizontal axis and 1 up. So if I were to come over here, the magnitude of this vector, which let's just call x, is going to be equal to square root of x1 squared, so we got 0 squared, plus, and then x2 squared, and in this case it's 1, so plus 1 squared. So if we type all that into our calculator, or at least I hope you're not using a calculator at this point, we get 1. So this one's good to go. And similarly, we can do the same for the blue vector. So over here, we know that this coordinate point goes 1 in the horizontal, but no vertically, so it's going to be 1, 0. So if I were to do the magnitude of this one, and we'll call this one y, and yes, this will get very confusing if I keep up this notation. And I guess I should put the kind of the double absolute signs on here. All right, so going back to the blue vector, we can go equals to the square root and the first component squared, so we got 1 squared, plus the second component squared, so we have 0 squared, and throw that into our calculator, and we get 1. And yes, I know it sounds silly throwing it into your calculator, but on an exam, I'd probably do that for some unknown reason. So we gave 2 examples of where it has length of 1. However, we still have the question, how many possible combinations of vectors have this? Well, if we're looking at purely just length 1, what we can do is actually, if we were to draw a circle all the way around, and yes, hopefully this will autocorrect a little bit better, we can have infinite number of vectors with length 1. For example, if I were to go to green, I can have this vector right here. It's going to be a combination of x1 and x2, but it'll still have length 1. Oops, didn't mean to zoom in like that. I can come down here, and again, this will also have length 1. So basically, you can go all the way around that circle with every vector having length 1. So for this one right here, there's actually an infinite amount of vectors that have length 1. All right, so going down, we have now norm equals 2. So the magnitude is 2. And just like before, what we can do is we can draw a circle all the way around. So we're going to go all the way to these points. And, oh, that doesn't look good at all. But at least the iPad kind of has my back and made it look a little bit better. All right, so that's not bad. So in this case, this right here is 2. We'll have 2 up here. We'll have -2. And then we'll have 2 down here. And just like before, we can have vectors going in any direction. So we can have one coming up like this. We can have, let's say, one going perfectly horizontal. We can even have one going horizontally in the other direction, like this. So just like before, for norm is equal to 2, there's actually infinite vectors or possibilities. There's an infinite amount of vectors that could have norm is equal to 2. And if I were to prove one really quick, well, we know that for this horizontal one, we know that it goes 2 horizontally and then 0 going across. So if we were to put this into our formula, so we go the norm of x is equal to the square root of the first component squared, so we got 2 squared, plus the second component squared, so 0 squared, put the square root over top. What we get is this is going to be equal to 2. And yes, I know I'm being really lazy picking the horizontal and vertical vectors, but let's be honest, that's how that's how you get the good grades. Anything lazy works perfectly. A grade is still a grade, a mark is still a mark. Who cares, as long as you get there. So now, the final part of the question is kind of the most interesting one. How many vectors have the norm 0? And as you guys know, I didn't draw a grid because this one's kind of a unique case. So for this one, what we're going to do is we're going to look strictly at the formula. So if we were to go, the norm of x is equal to the square root, and remember, we're only sticking in 2 dimensions. It's going to be x1 squared plus x2 squared. So if we look really quick, both of those components are squared. So no matter what, those are both going to be positive values in the squares. So the only way that this equation will ever equal to 0, there's only one possible solution. It's x1 is equal to x2, which is equal to 0. So for this case, there's only one vector with norm 0, so one vector. And in this case, it's the 0 vector. And this is the only vector that'll ever have norm or a magnitude of 0. And that can just be proven by looking at the math. The only way that equation is going to equal 0 is if x1 is equal to x2 which is 0. All right, so moving on, we have consider R2 again. So again, we're sticking with 2 dimensions, but now we're going to talk about Euclidean distance. So the formula right there is x minus y. How many vectors have x minus y is equal to 1? Well, just kind of like before, there's going to be an infinite amount of vectors. Now, how can we pick one of these vectors? Well, it's pretty simple. All I want to do to make this really easy for myself is, let's say I have a point here, or sorry, yeah, let's say we have this point, and this point is located at 1. And we want the distance between 2 points to be 1. So if we know this point right here, I know that the scale of the graph is going to be off, but if this point is 2, we know that this distance from here to here is equal to 1 right here. So all we have to do is say, okay, well, this will be vector 1, this orange one, and this one right here. If just looking by it, doesn't even matter what y is, because what we'll have is we'll just put y. So the coordinates at this point are 1 comma y, and we have the second vector, which will go from here over to here, and the coordinates of this one are 2 comma y. So again, as you guys will see, I'm kind of cheating with this. If I were to plug these values into the formula below, so if I were to go row, this is how I do row. I know I put a little tail that everyone thinks is kind of weird. So we know that this is going to be equal to the square root of x1 minus y1 squared. So in this case, it doesn't matter which one you pick because they're both going to cancel. So let's start with the orange one. So let's say 1 minus 2 squared, and then plus the second components minus each other. And in this case, if they're both at y, what's going to happen is we're going to have y minus y squared. And if I put this over top, just finish off the square root, throw that in, well, the y minus y squared, well, that's just 0 squared. So this kind of cancels out. We're left with negative 1 squared, which is 1, and then the square root of 1 is 1. So in this case, row of x and y is going to be equal to 1. And if we go up, well, yes, that's what we're looking for. So perfect. And again, there's infinite amount of combinations. So instead of doing a horizontal one like this, what I could have done is I could have picked a point, let's say a point here and a point here, and the distance between these two like this is going to be equal to 1. So let's say that these values are at negative 1, and then down here is negative 2, and then this is the value x. And then I could have just made 2 more vectors. So like something going like this. And then I could have had a second one going downwards like this. And you can do this kind of rotating this all the way around the coordinate system. So again, there's going to be infinite vectors for this case. So infinite vectors. All right. So the second part of the question, how many vectors have a distance of 0? Well, again, we have to look at the formula for this one. So what I'm going to do is I'm just going to write the formula really quick. So x minus y is equal to, and I don't think I left myself enough room for that, but we go x1 minus y1 squared plus x2 minus y2 squared. So if we look at this formula, what we need is we need x1 minus y1 to equal 0, and same on the other side. So the only way that this is going to happen is if the vectors are in the exact same position. So let's say I got vector 1 coming like this, right here, and its points are x comma y. Well, the only time that the distance between these two vectors are going to be 0 is if they're the same vector. So my second vector would also kind of overlap over top here and be the same one. And that you guys can very quickly visually see that yes, the distance between those two vectors is going to be 0. They overlap each other at the end. But now we have to ask ourselves, how many combinations of vectors have the distance between them equal to 0? And like before, there's actually an infinite amount, infinite vectors. And the only reason is because I could have 2 overlapping vectors like I did above, Or let's say I can have them down here, something like this, where I have the first one, and then I have the second one. So as you guys can see, I can just rotate those two vectors all the way around the coordinate system to give myself infinite amount of vectors. So that's how many vectors have Euclidean distance of 0. So now we're going to start getting into the fun stuff. So it says consider R3. So now we're talking about 3 dimensions with the Euclidean dot product. Find 3 vectors perpendicular to, and then the first one, I guess, is this x is equal to 1, 0, 0. So perpendicular. So something is perpendicular. If I have 2 vectors, and the best way I can do this is to draw. So let's say that I have a vector here, like this, and then I have a second vector that comes out like this. We know that in order for these two to be perpendicular to each other, the angle must be 90 degrees. So theta is equal to 90 degrees. And if we look back at our dot product, remember we have x dot y is equal to the magnitude of x multiplied by the magnitude of y times cosine of theta. Now, if we throw 90 degrees into here, so for theta equals 90, this actually cancels out because cosine of 90 is 0. So if 2 vectors are perpendicular, what we say is that x dot y is equal to 0. And that's why I said that the cosine of theta is so important in this case. So if we were to expand our vector out, so let's say that we just assume our vector y is going to be equal to, I'm just going to put y1, comma y2, comma y3. If I were to do x dot y, so I'm going to do this in different color just to kind of make it a little bit brighter. So we got x dot y is going to be equal to, so it's going to be x1, which we see up there is 1, so we're going to have 1, times y1, which we're just going to put as y1, plus x2, which is 0, times y2, and then finally we have x3, which is also 0, times y3, and all this to be perpendicular must be equal to 0. So from here, it's really, really easy to see that no matter, if I were to look at these two, the y2 and the y3, it doesn't matter what those are, because if we're multiplying them by 0, they'll be 0. The only limiting factor we have to consider is this y1. So for a vector to be perpendicular, we just need that y1 to be 0. And y2 and y3 could be anything else. So if I were to just look at vectors, I can say, let's go y is equal to, as long as the first one would go 0, and we can put any other numbers. So we can go 5, 6. We can go y is equal to, remember the first one's 0, and we can do anything. So we can go 1, -2. And then a third one would be y is equal to 0, let's go 3, 5. So these are all perpendicular because if we were to substitute these values in, we got x dot y is equal to 0. So as long as that y1 is 0, y2 and y3 could be anything that they want. And now this one is kind of even more interesting, where it's x is equal to 0, 0, 0. So again, it wants a perpendicular. So if we were to go x dot y, assuming y is just equal to y1, y2, y3, we got 0 times y1 plus 0 times y2 plus 0 times y3. And if they're perpendicular, this must be equal to 0. So since we have zeros in all 3 parts of these right here, it doesn't matter what y1, y2, or y3 are. And if y2, y1, and y3 can be anything, that means that any vector possible, so any vector dot with the 0 vector will be perpendicular. So from this case right here, we have an infinite amount of vectors that when we dot it with the 0 vector will give a perpendicular vector because it doesn't matter. So if I were to go up to the top really quick, let's just say I go y1 is equal to 6, y2 is equal to 4, and then y3 is equal to, let's just say 3. Well, 0 times 6, that's going to be 0. 0 times 4, that's going to be 0. And then 0 times 3, that's going to be 0. And if I sum all three of these up, well, what do you know? It's equal to 0, meaning it's perpendicular. So that's it for the quiz. Again, hopefully a lot of it was just nice review from Eng 130. At least that's what I'm counting on. Again, the only thing that's really different was the terminology. But once you guys get the new terminology down, it's a piece of cake. And as you guys can see from the calculations, they're pretty simple. And this is what to expect on the midterm. So if the calculations are easy here, hopefully they'll be easy on the midterm, and you guys will all be happy with your good marks. So that concludes quiz number 4. In quiz number 5, we're going to continue on with some a bit more advanced operations. So I will see you guys in quiz number 5.